Alright, so the end of the Unit 11 notes is on something called LeChatelier's principle. Alright, and that's some dude's name that came up with this idea. So if you think back to equilibrium, when we have a reaction at equilibrium, then both the forward reaction and the reverse reaction, their rates are equal. So remember, at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, right? And the concentrations of the substances in the reaction are no longer changing. They are constant, all right? So the whole rate forward reaction, rate reverse reaction, that's the important part here. So LeChatelier's principle is when a stress is applied to a reaction at equilibrium, the position of the equilibrium will change to compensate for that stress. Meaning, the reaction will shift to favor the reactants, as in it'll shift left, or to favor the products, shift right. And it's the actual position of equilibrium. It's which of those reactions, the forward reaction or the reverse reaction, it's kind of taking over, is being favored to compensate for one of three stresses. So we have three ways to apply stress. We can change the amount of a gaseous or aqueous reactant or product. So change the amount of a reactant or product, but remember, we only care about gas and aqueous. We don't care about liquid or solid for equilibrium. So if we change a liquid or solid, it's not going to do anything. We can change the pressure or volume of the reaction container, or we can change the temperature of the reaction. So I'm going to go through each one of these and describe how the reaction compensates for these stresses. So the first one is to change the amount of a reactant or a product. Now, this only affects the equilibrium if the reactant or product is gas or aqueous. I already mentioned that. So no shift if the substance you are changing is a solid or a liquid. And one thing I want to point out is this, changing the amount of the reactant or product, there is no effect on the K value, on the equilibrium constant. Remember, equilibrium constant is a constant for each reaction. So changing the amounts of one of our reactants or products isn't going to change what that K value is. So if you add something, you need to shift away from that addition to compensate for it. So if we add something, we're going to shift away. As in, if we add something on the reactant side or the left, we are going to shift towards the product side or the right. And vice versa. If we remove something, we now have less of whatever that something was on whatever side it was on, so we're going to shift toward that removal. So if you remove a reactant, we are going to shift toward the reactant side or to the left. If we remove a product, we're going to shift toward the product side or to the right. So now we're going to go through an example of how this of looking at a reaction, and we're going to look at a couple different changes and seeing how the equilibrium position will shift. So this is in your packet. Oh, nope, sorry, I lied. I'm going to skip to that. There we go. Nope, here's an example. So, looking at this example, we have this reaction. We are going to add N2. So we're adding something on the reactant side. So now there's more of this. So it's going to shift away from it to compensate. So we're going to shift to the right. And you can just use an arrow if you want. Okay? Let me erase that. All right, adding NH3. Now we're adding something on the product side. So we're going to, since we're adding, we're going to shift away from the addition. So we're going to shift to the left. And then with the last one, now we're removing NH3. since we're taking away some of this, the reaction needs to shift towards that removal to compensate for that change. All right, with the next set of examples, or the next example, the next reaction, we're going to remove CO2. So we always shift toward removals. So we're going to shift to the right. Next one, we're going to add CaO. Well, CaO is on the right side, so you would think you would shift away from that addition, but it is a solid substance. Solids and liquids do not go in the equilibrium expression. Therefore, they do not affect the equilibrium position if you do anything to them. So with this, there is no shift. It doesn't do anything. And the same thing with CaCO3. That is also a solid. So doing anything to that, no shift. Nada. Does nothing. All right, so let's go back to, okay, that was changing the reactant or the product. Now we're going to talk about how if we change pressure or volume of the reaction container, how it affects the equilibrium position. So, if we increase pressure, that is the same as decreasing volume. Boyle's law taught us that back in gas laws in Unit 8. So if we're decreasing volume or increasing pressure, there's now less space available for the molecules to react. So, since there's less space, the reaction is going to shift to the side with the least number of gas molecules. So if you decrease volume, if you have less space from decreasing volume or increasing pressure, you're going to go to the side with the least number of gas molecules. And only the gas molecules are important here. So even though aqueous substances go in the equilibrium expression, for pressure and volume changes, all we care about are gases. Now if we do the opposite, if we decrease pressure, which we know is the same as increasing volume, we now have more space available for the molecules to react. So the reaction is going to shift to the side which has the most number of gas molecules. So you have to look at the reaction. You have to look at the left side. You have to look at the right side. You first have to count how many gas molecules are on each side to then look at how these pressure and volume changes are going to affect the equilibrium position. So let's do some examples of that. So we're looking at this now. So we have this first reaction, and I've already counted the number of molecules for you, but the way this was found was you take the coefficients of the gas substances on each side, and you add them together on each side. So here we have 1 and 2 and 3 H2. 1 and 3 makes 4. On the right side, we only have 2 NH3, so there's only 2 gas molecules. And all of these were gases, so it was really easy to count. So we're going to decrease the volume, which means we're going to go to which is the same as increasing pressure. So we're going to go to the side with the least gas molecules. So the one that has the least number of gas molecules is the right, so we're going to shift to the right. If we increase the volume, which we know to be the same as decreasing pressure, we're going to shift to the side with the most number of gas molecules, which is the left. I'm looking at the second reaction. On the left side, there are no gas molecules, so we're sitting at 0. And on the right, there's only 1 mole of gases. There's only 1 gas molecule on the right. So if we decrease the volume, which we know to be the same as increasing pressure, we always shift to the side with the least gas molecules, which is the left in this case. So even though there's none on the left, 0 is less than 1, so therefore we shift to the left. Increasing volume container is the same as decreasing pressure, so we're going to shift to the right to go towards the side with more gas molecules. And 1 is greater than 0, so we have more gas molecules on the product side or the right. And the third type of stress was changing temperature. Now, for temperature, hold on, let me go back. For changing the pressure or volume of the reaction container, this also does not affect K. Affect the K value, okay? Does not affect K. And one more thing I want to say about this, and only because it's one of the examples you're going to do later, is if you add an inert gas, like a noble gas, there is no shift. Okay? Adding an inert gas changes the pressure of the entire thing. It changes the pressure of both sides of the reaction equally. So since both sides are changing the same amount, there's not going to be a change overall to the equilibrium. So you're going to have an example like that later. So I just wanted to point that out to you. Alrighty, now for temperature. So with temperature changes, we have if we're changing temperature, we have to look first at, is the reaction exothermic or endothermic? All right? Excuse me. If it's exothermic, energy or heat is being released. Since it's being released, it is technically a product because we're producing it. Now, we're going to treat that change of temperature as an addition or removal of heat, which we're treating as a product. So, if we increase temperature, we're adding heat, so we're adding a product, so we shift away from the products or to the left. If we decrease temperature, we're removing a product, we're removing heat, so we're going to shift toward the products or to the right. For an endothermic reaction, energy or heat is absorbed, so we're adding it to the reaction, so it's a reactant. So we're going to treat that as, we're going to treat the change of temperature as an addition or removal of heat acting as a reactant. So if we increase temperature, that's adding heat, we're adding a reactant, we shift away from the reactant side toward the products, or shift right. If we decrease temperature, that's removing our heat as a reactant, so we're going to shift toward that removal, or to the left, toward the reactants. Now, changing the amounts of the reactants or products and changing changing pressure and volume, those did not have any effect on K. Changing temperature, however, it will change K as well. Because remember, K is temperature dependent. So if you change the temperature, it's going to change what that constant is. So now let's look at how changing temperature affects K. Now remember, K is the products over the reactants. So for exothermic reactions, when we increase temperature, we're shifting toward the reactants. Okay, so the reactant numbers are going up and the product numbers are going down. So K overall is decreasing when we increase temperature of an exothermic reaction. And then the opposite happens when we decrease temperature of an exothermic reaction. All right, if you decrease temperature of an exothermic, the products are now increasing, so the top number of my K value is going up, so the K value is also increasing. Now with an endothermic reaction, you have to think about which way you're shifting. If we're increasing temperature, we're shifting to the right, and K increases because my products are going up. And then decreasing temperature, you're going to shift to the left, which means K will decrease. Do you notice how shifting to the right for both of them causes K to increase? For both types of reactions, exo and endo, if you shift to the right, K is going to go up. And if you shift to the left, K is going to go down. But what causes us to shift to the left or to the right is different if it's endo or exo, because heat is being treated differently. Sorry for the bell. That is on the video, not in real life. All right. So let's do an example of temperature stuff. All right, now remember, only temperature will change K. So if it's changing the concentration of something, it will not change the K value. Your homework asks you how K is affected by each one of the changes you're going to look at. So only the ones with K should have, or only the ones with temperature should have a change in K. Oh, hey, look at that. I already had it all written out about temperature affecting K. Cool. Didn't realize I had that typed already. All right, so now we have these last few examples in the packet. So looking at the first reaction, first of all, we need to identify if it's endothermic or exothermic. So we look at the delta H value. Since delta H for this first one is negative, that makes it exothermic. So that means heat is a product. So we can go ahead and write plus heat on the product side. So if we increase temperature, we're increasing a product, so we're going to shift away from that product or to the left. And if we decrease temperature for this reaction, that's like removing a product, so we shift toward it or to the right. Let's look at how that is going to affect K. If we shift to the left, K always goes down. And if we shift to the right, then K is going up. Now for the second reaction, we have a positive delta H value, so that means it's endo. So that means heat is a reactant. So we're going to put heat on the reactant side. So if we increase temperature, we're adding a reactant, so we're going to shift away from that addition toward the products. Boom. And if we remove temperature, we decrease temperature, we're removing heat, so we're removing a reactant, so we're going to shift towards that side. And again, when we shift to the right, K is increasing. When we shift to the left, K is decreasing. Only if the shifting is due to a temperature change. All right? So you have you have a chart in your packet that I want you to complete, and the answers are with Mrs. Kuzma or the sub, so you can check your answers after you complete them. And then you're going to work on the worksheet that you got, which is a big old chart. Remember, you're going to be looking at how K is affected for everything, but remember, only temperature affects K. Then if you're finished with all of that, you are going to work on your SOL review packet, which I instructed you to bring to every class. All right, I will see you guys at the end of the week. Please be good. Do your work. See you later.